Hello everyone, my name is Brant Kudrowski and this organic chemistry video deals with factors affecting the SN2 mechanism, leaving group quality. The SN2 reaction is affected by a number of different factors. In the first video, we looked at previously here how substitution of the alkyl halide impacts the SN2 reaction, so what kind of substitution is present there. This video deals with leaving group quality, so it addresses issues of the identity of X and how that influences the reaction. In subsequent videos, we'll look at the strength of the nucleophile and the effective reaction solvent. The SN2 reaction occurs in a single step. The nucleophile attacks the carbon and the leaving group leaves in one step, and since it's the only step, it's the rate determining step. That's a key factor, that the leaving group leaves in the rate determining step. Therefore, leaving group quality is going to affect the SN2 rate. The ability of that group to leave will influence how fast the SN2 reaction happens. A better leaving group, therefore, gives a faster SN2 reaction. Good leaving groups are weak bases, and the weaker the better. X-, when it leaves, should be nice and stable and should not be a strong base, should be a weak base. For the reaction to favor products, the leaving group X- should be a weaker base than the starting nucleophile. Reactions like to go from strong base to weak base, and if the reaction is set up that way, then the products will be favored. This slide will cover some examples of good and bad leaving groups. The first table is going to include some examples of good leaving groups, and in this table I've got columns for starting material, the leaving group's conjugate acid, and the pKa of the conjugate acid. These last couple of columns are in here because the leaving group's basicity is so important in determining how good of a leaving group it is. So the first example we'll look at will be alkyl halides that contain a chlorine. So the chloride here would be the leaving group. Cl leaves is Cl-, Cl- is the leaving group. The conjugate acid of Cl- is HCl, and HCl is a very strong acid. It has a pKa value of -7. That means that the Cl- is a very weak base. There's an inverse relationship between base and conjugate acid, and if something is a very strong acid, for example, its conjugate base, Cl- in this case, would be very weak. So Cl- is an example of a very weak base. That makes it a good leaving group. The next example is bromine. So bromine has some similar characteristics. Alkyl bromides have a Br-, that's a leaving group, and HBr is also a very strong acid. It's an even stronger acid than HCl. Its pKa value is -9, whereas the HCl has a pKa of -7. So the reason that bromine then is a better leaving group is that Br- is a weaker base than Cl-. That has to do with the size of the atom. Br- is a larger atom than Cl-, and negative charges are more stable on larger atoms. That logic continues in looking at alkyl iodides. So when the leaving group is I- is a very weak base because Hi is a very strong acid. Hi has a pKa value of -10, which is even stronger than the others above. I- is the best leaving group among these three halogens. Iodide is the best, bromide is second best, chloride is third best. Another really common leaving group that we're going to see more of later on in the semester is an R group that has a protonated alcohol, so an O with two H's and a formal positive charge on the oxygen. The reason this is a really good leaving group is when this bond breaks and that leaving group leaves, the leaving group is water, and water is a fairly weak base. The conjugate acid of the leaving group is H3O+, shown here. That's a strong acid. It has a pKa value of -1.7. It's not quite as strong an acid as Hi, so this H2O is not quite as good a leaving group as I-, but it's still classified as a very good leaving group. So the big message here is that weak bases are good. In the next table, we're going to take a look at some examples of poor leaving groups. So these are bad leaving groups, and we'll see why here in a little bit. The first example we're going to look at is fluorine. Alkyl fluorides, for example, are groups attached to fluorine. The leaving group is F-, and F-'s conjugate acid is HF. Now, HF is not a weak acid, but it's not nearly as strong as the acids in this previous table over here, which means that F- is actually a fairly strong base compared to the bases in this table up here. The pKa value of HF is 3.2, and that's not nearly as acidic as the acids in the upper table. The bottom line is F- is a somewhat strong base, and that makes it a somewhat poor leaving group. F- is a bit stronger base than some of these others due to atom size. F- is a smaller atom than Cl-, and that dictates its basicity. It's a stronger base than Cl- because of that. Here's another example of a poor leaving group, OH leaving is OH minus. OH minus is a strong base. The conjugate acid of OH minus is H2O, and that's not a very strong acid. Water has pKa value of 14 or 15.7, depending on the reference material that you're looking at, but any way you look at it, it's not a strong acid, and therefore this base is fairly strong, and it's not a good leaving group. Here's another example of a very poor leaving group. Any kind of neutral nitrogen is going to be a rather poor leaving group, because nitrogen, negatively charged nitrogen like this, is quite a strong base. The conjugate acid of the nitrogen species here has a pKa value of 38, which is not a strong acid at all, which means that this is a very strong base. And then as an example of a very, very poor leaving group, any kind of alkyl group, leaving as an R minus would be just a really, really strong base. This is a very, very weak acid at 50. And this is not a comprehensive list of poor leaving groups. There are many, many other examples of poor leaving groups. But up here in the good leaving group category, these are pretty much what you're going to see for alkyl halides. Chloride, bromide, and iodide as leaving groups, but not fluoride. Fluorine is just too strongly basic when it leaves, so it doesn't make a good leaving group. To summarize, strong bases are poor leaving groups.